Hey everyone, thanks for coming today. I'm Rob. I have been working on VLLM and llm-d for the last couple of years. I joined Red Hat about 9.5 months ago by way of acquisition from Neural Magic, where I led our overall engineering team and a lot of our efforts in those upstream projects. And now I'm a member of the technical staff at Red Hat on the inference engineering team. Today I'm going to talk a little bit about distributed inference with llm-d. I'll talk a little bit about how llm-d fits into an enterprise's AI inference serving architecture and some of the features that we have that help to optimize inference at a cluster scale. So as we think about Red Hat's overall inference platform, we see a variety of different layers of the stack. At the bottom layer, whenever we're looking at LLMs, typically these are going to run on hardware accelerators. So obviously NVIDIA GPUs, AMD GPUs, Google TPUs are some of the most popular accelerators that are out there in the market. And we seek to optimize inference across all of these different hardware backends. VLLM, which many of you might be familiar with, is a very, very common, one of the probably the most broadly deployed inference server in the market. And VLLM's job is to really abstract that hardware accelerator and provide a kind of Rosetta Stone piece of technology that allows all the different models that are out in the ecosystem to get mapped onto all the different accelerators that are out there in the market. So VLLM is a really important piece of software that's really responsible for being that kind of Rosetta Stone for enabling all the different models to run on all the different accelerators. Obviously, we have the model layer. There's been lots of activity in the open source model space. Whether it's Meta with their Llama series, OpenAI with GPT OSS, Mistral, Google, obviously IBM Granite, and there's lots of action at that layer. But really, when we talk about llm-d, we're looking at a whole cluster of VLLMs, and we're taking a dependency on Kubernetes, and we're looking at how can we optimize a whole cluster of VLLM servers, running inside of the Kubernetes framework to get the best possible performance over a whole cluster of VLLMs that are running. So I'll just start. As I mentioned, VLLM is really that de facto standard for inference. We support all the different really important models running across all the really important accelerators that are in the market. So VLLM sits at the centerpiece of the llm-d architecture that we'll talk about a little bit later. And its job is to really optimize one particular node or one particular GPU server to make it go as efficiently as possible for all the different models that might matter. And when we look at llm-d, the overall idea is to try to get the best possible performance when we're running a cluster of VLLMs. And you might ask the question of why is there an opportunity to build an LLM specific, Kubernetes serving platform, right? Kubernetes for a very long time has been solving the problem of scaling out a cluster of services, right? The tried and true concepts of a deployment and a service. It's very, very common to spin up a few replicas of a server, put a service load balancer in front of that service, and distribute the load and scale out a deployment in that way, right? However, traditional Kubernetes services are kind of built around traditional HTTP requests, which have the following properties: they're fast, they're uniform, they're cheap. So at a toy example, a microservice load balancer, is able to, distribute load across the cluster in a very, very even way by just doing something naive like round robin or random load balancing to those pods. And it turns out that if the requests are fast, uniform, and cheap, this pretty much, distributes the load evenly to all the different pods. However, when we look at LLM requests, these implicit assumptions are just completely untrue when you look at the LLM workload. In particular, LLM requests are really slow. A particular request can take over a minute, as you think about generating one token at a time. And if you generate 1,000 tokens, the overall time for the request is the time to generate one token times 1,000. And so it's very easy for individual requests to take a super long time. In addition, we have really, really non-uniform requests, where you can sometimes have a really short prompt with a really long generation, or in a RAG use case, you can have a really, really, really long prompt and a short generation phase. And lastly, particular replicas of VLM can be orders of magnitude faster at processing an individual request due to the temporal locality of most LLM services, where if you think about interacting with a chatbot or an agentic application where the model is executing a tool and then getting the results of that tool back, you often have a multi-turn kind of conversation with the model, and it's very important to be able to route those to the replicas that have the hot caches associated with those requests to be able to get optimal performance. So the key assumptions of a deployment in service, which are, you can spin up more replicas and just naively load balance in front of those replicas, kind of falls apart when we look at the LLM workload. And we're leaving a lot on the table in terms of optimizing performance if we don't take advantage of these unique properties of LLMs to, try to get the best performance. And so as we look at llm-d, the overall idea with llm-d is to take advantage of the key optimizations that are being used by large labs for serving their models that exploit the unique properties of the LLM service and bring them into the Kubernetes framework. So in particular, we take a dependency on Inference Gateway API extension, which builds on top of Gateway API, which is the sort of future of Kubernetes networking, and we build on top of the existing primitives that have been coming into the Kubernetes ecosystem. So as an example, the request will come into Gateway in the same way that any HTTP service that's building on top of Gateway will work. In OpenShift, this uses Istio and Envoy. In a cloud environment, this could be GKE Gateway or whatever gateway vendored by the by a cloud provider. And Gateway will call out to an inference scheduler. And this inference scheduler is where we inject a lot of the LLM specific logic. So inference scheduler can have an understanding of which prefix caches are available in which VLLM pod. It can understand the amount of load on each VLLM pod. It can understand if VLM is configured in a more complicated deployment pattern, for instance, prefill, decode, disaggregation. It can understand if VLM is working with prefix cache offloading or not. And that inference scheduler makes the decision about which pod the request should be routed to. Then we send it back to the gateway, and then the gateway send the request off to the inference pool, and the inference pool, can be configured in a variety of different ways. It can be a standard deployment of VLM. It could be a disaggregated deployment. We'll talk a little bit about what that means in a few minutes. It could be leveraging more advanced features like KV cache offloading that are more complicated deployment patterns for VLM. So this is the architecture. It's actually quite simple. I think the overall idea is to try to leverage the existing, load balancers and gateway API that already exists in the Kubernetes ecosystem and bring these, interesting concepts of the specifics of the LLM workload into that world. And so to explain a little bit more about this, I'll talk about some of the features that llm-d enables. We've been calling these well-lit paths. These are generally patterns that we're aware of in the ecosystem where, large model providers are leveraging these techniques to get more performance. We saw, for instance, with DeepSeek's Open Source Week, they're leveraging a lot of these overall concepts in their deployment pattern. And with llm-d, it's our goal to kind of take these concepts that we know are being used by high-scale deployments of VLLM and of LLM services and bring those into the Kubernetes framework. So I'll talk through a couple of different patterns that the llm-d design enables, which, again, are all trying to optimize the performance and get more out of your VLM cluster. So we'll talk about intelligent inference scheduling, which is, basically doing better load balancing. We'll talk about prefill, decode, disaggregation, which is the technique for improving the performance of the prefill and decode phase by specializing replicas for prefill and decode. We'll talk about KV cache management, which is about using the whole memory hierarchy and storage hierarchy available in the cluster to increase the cache size And then we'll talk about wide expert parallelism, which is a technique that's really useful for serving some of the state-of-the-art models that we have today. So to start with intelligent inference scheduling, the first kind of feature that this architecture enables is for us to do better load balancing than what you can get from standard round robin. So I'll give two examples of this. The first is what we call Prefix-Aware routing. It's very, very common, and this is one of the things I mentioned in the upfront section. It's very, very common for LLM requests to have temporal locality. And basically what this means is it's very common for the same prompt to be sent to the model over and over and over again in short succession. Think about when you're interacting with a chatbot, you might send the first prompt, the model will respond, then you'll respond to the model's response and send that entire context back to the model over and over and over again. Or you can think about a case like an agentic use case where the model maybe is executing, decides it needs to call a tool, it, calls the tool, gets the result back from the tool, continues generating. And every time you're sending the data back to the model, you're sending the same prompt with a bit more context over and over and over again. And so VLLM has a feature called prefix caching, which basically allows us to skip computing the prompt if the KV caches for that prompt are resident in VLLM's GPU RAM. And so one of the things that we really, really want to do inside of the cluster is to route requests to the pod that have the prefix cache available in that pod. And so this is one of the features that we get out of Prefix-Aware routing, where the request comes into the gateway sends it off to the endpoint picker, which is the inference scheduler, and the endpoint picker can be configured to either read the KV events from VLLM, which is kind of streaming back the state of the prefix cache to the endpoint picker, or the endpoint picker can maintain an approximate understanding of the prefix tree in each one of these VLLM pods. Based on that information, the endpoint picker can say, okay, pod A has this prefix cache, let's route the request to pod A. And so you can see how this does better than random load balancing, where if you just had a standard Kubernetes service here, we would route the request to one of these three pods randomly and miss out on the ability to skip computing the prompt for that individual request. And especially as we start looking at longer and longer context models, which is absolutely the trend, especially for agentic applications, this optimization becomes critical for balancing load as best as possible. Another example of a technique that we have is what we call load-aware routing. So I mentioned before, there's a lot of heterogeneity in LLM requests that are hitting a server. And so a thing that can happen is if a server gets unlucky where it gets a super long prompt or it gets a really, really long generation phase, the server can become overloaded and slow down. And so one of the other techniques that we have inside of llm-d is that endpoint picker is constantly probing the metrics on each one of the pod to understand the current state of the load. How many requests are in the waiting queue? How many requests are in the running queue? What is the KV cache utilization? And the endpoint picker is able to send the request to the pod that has the lowest load. And so this allows us to avoid hotspots in the cluster where certain pods get overloaded, which is something that can happen, especially when we look at heterogeneous requests where maybe you have multiple tenants that are hitting the same kind of endpoint with different overall request patterns. And so intelligent inference scheduling is an example of how we can do better than naive load balancing by understanding the specifics of the LLM workload, whether it's, okay, we need to take advantage of the prefix caching, which is a really, really big optimization, or, we want to deal with the fact that there's a lot of heterogeneity in the requests and, balance the load evenly across the load-aware scheduler. So anyways, these are two examples of, how we can do better than just naive load balancing by, hooking into the request flow inside of Gateway. All right. And another example of a technique that we have inside of llm-d where we want to do better than just a naive scale out is a technique that we call Prefill decode disaggregation. And in this case, I'm looking more at that inference pool, right? So in this design that we have here, I talked a little bit about how the intelligent inference scheduler is a component that can, help to better balance load within the inference pool. But another thing that we can do when we look at the cluster scale is to configure the VLLM pods differently. And it turns out that when we look at the LLM inference workload, there's two phases to the request. So the first phase is what's called prefill. Prefill is when we process the prompt, right? So during the inference phase, the request comes into the server, and we have to compute the KVs for all of the prompt tokens. This is a very what's called compute bound workload. So we're bottlenecked by the amount of flops available on the GPU. Then after the prefill has been computed, we move on to the generation phase where we're generating new tokens. This is called the decode phase of LLM inference. And the decode phase is what's called memory bandwidth bound, where the computation is bounded by how fast the data can move from the HBM into the on-chip memory. And these computations are very, very, very different. And so one of the things that we can do to exploit these unique properties is to configure the prefill pod and decode pod differently. Where in the decode case, maybe we want to use more tensor parallelism. And in the prefill case, we maybe want to use less tensor parallelism as an example of a way to configure the pods differently. When we look at models like DeepSeek as well, there's even more complicated things where we may want to deploy with data parallel attention and expert parallel MLP layer, which really, really starts to flex the need for PD disaggregation in those environments. And so in llm-d, we actually implement this prefill decode disaggregation phase. And so the way that the request works is it comes into the gateway, we send the request off to the scheduler decides to schedule the request with PD disaggregation. And then we send it off to the decode pod. The decode pod has a sidecar which facilitates the transaction. The sidecar forwards the request off to the prefill pod. The prefill pod generates or executes the prompt and returns what we call KV transfer metadata back to the sidecar. The sidecar then forwards the request to the decode worker. The decode worker executes an RDMA transaction to pull the KVs from the prefill pod, and then the decode pod processes the decode. And so, as you can see, using this mechanism where the scheduler is kind of aware of the fact that we've configured the cluster, we've configured the inference pool with prefill pods and decode pods, and by using this wire protocol for KV transfer and leveraging the NIXL technology, which executes the RDMA transaction, we're able to kind of successfully disaggregate the prefill and decode phase of inference, and which allows us to optimize the prefill pods for prefill work and optimize the decode pods for decode work. And so this really heavily relies on some features in VLLM, which is called the PD disaggregation or KV transfer subsystem inside of VLLM. We use NIXL, which is the NVIDIA Inference Transfer Library, which is a wrapper around UCX, which is a high performance networking library, which will use InfiniBand or Rocky or TCP to actually move the KVs. And inside of VLM, we use GPU direct RDMA, where the data will be transferred directly from the GPU memory of the prefill worker to the GPU memory of the decode worker with zero copy and without having the kernel involved. So this is a really important feature in VLLM that enables this kind of mechanism to make that happen as efficiently as possible. And this is a really flexible deployment. So we can do heterogeneous tensor parallelism where the decode worker can have more parallelism, the prefill worker can have less parallelism, and it's dynamic and lazy. So every decode worker can talk to every prefill worker. And in general, this PD disaggregation leads to a really nice performance win. Even for like a small model like GPT OSS 20B, we're able to offer 20 to 40% overall improvements in the latency for the same level of throughput. This is what's called a Pareto chart, where the x-axis shows the latency, so the tokens per second per user. The y-axis shows the tokens per second per GPU, so the throughput. And in general, you want to be up and to the right. Is the Pareto frontier, and what we can see is that the latency in the disaggregated case for a similar level of throughput is much improved. Another technique that we have in llm-d is called KV cache management. I think this theme is hopefully coming through, where we're trying to take advantage of the unique properties of the transformer architecture, and specifically the KV cache is a really critical component of this, whether it's the prefix cache aware routing whether it's the PD disaggregation and the KV transfers. But another kind of technique that we can use is to try to just increase the size of the KV cache pool that we have inside of the cluster. So by default, VLLM uses the GPU RAM, and we keep the KVs resident in the GPU memory until within a least recently used cache, right? So once we run out of space, we evict the KVs, and then future requests will not be able to, we'll have to recompute those KVs, right? And so one of the key observations that we have is that in particular for GPU nodes, like you look at an H200 node, there's a lot of CPU RAM attached to these nodes, and it's really not being used for much. There's a little bit of CPU state that we have on the VLM side, but really it's like very, very, very small in comparison to the amount of RAM available, like CPU RAM available on these nodes. And so one of the features that we built into VLM is a native CPU KV cache offload. So basically, rather than evicting the KV caches from GPU RAM immediately, we can evict these KV caches to CPU RAM. And what this allows is for us to basically increase the KV cache size even more and keep the amount of time that we're keeping the KV caches resident in RAM longer and longer and longer. And so this allows us to effectively just increase the amount of size, and it's much more efficient to just pull the KV caches from CPU RAM into the GPU RAM than it is to recompute the whole prompt. And so the various other components of the llm-d system, for instance, the endpoint picker inference scheduler, needs to be aware of the fact that we're running in CPU KV cache mode, for instance. But this is a really important feature that we know is being used by a lot of large providers, which helps us to just increase the chance that we get a KV cache hit and allow the data to stay resident in RAM for longer and longer. Another thing we've been working on with some partners, such as like Weka, is offloading to remote storage. So in addition to CPU RAM, there's also a variety of GPU direct storage vendors that have emerged to, which basically allows us to offload the KV caches, not just to local CPU RAM, but to remote SSDs. And those remote SSDs can get connected directly into the GPU memory as well, which allows us to also have a, a storage tier, which, splits across all of the pods. So anyways, this is a continuous optimization. I think the CPU RAM stuff is something that we're likely going to see in almost every deployment of llm-d, and something that will, it's kind of like something that should always be on as a feature. The remote storage is a little bit more complicated, so it's potentially something that we will, use in more selective cases. But in general, the overall idea of using all of the cluster resources to keep the KV caches resident in RAM is another kind of key feature. The last thing I wanted to talk about as a kind of optimization that we currently are working on in llm-d is on mixture of experts models. So a really key trend in 2025 has been the shift from dense models like Llama 3 towards sparse mixture of experts models like DeepSeek or GPT-OSS or Qwen 3 or TiMi-K2 or Llama 4. And the key piece is inside of the MLP layer, so the feed-forward network, inside of the model, rather than using just one MLP, instead, each token gets routed to one of n experts, and these experts are sparse. So basically, rather than having just one set of feed-forward networks, we have n different feed-forward networks, and each token gets routed, to one of the n experts, right? And there's a lot of really interesting optimizations that can be done to exploit this sparse mixture of experts architecture, especially when used in combination with Prefill decode disaggregation. So as an example, rather than using Tensor Parallelism, which is the way to deploy the dense models, we are able to actually use something called DPEP. And DPEP basically does data parallel for attention. So each request gets routed to one of the n ranks, and attention happens independently for each one of the requests. We have a dispatch operation, which after each token is gets routed, we send the token to one of the expert ranks. So basically each expert in the model gets put on a different rank, as opposed to sharding the individual experts. And so this dispatch operation basically takes every token and sends it to the rank that has that expert. Then the experts execute, and after the experts are done, we call this combine operation, which basically sends the token back from the expert back to its original DP rank. And this technique allows us to actually deploy the model over multiple nodes. So if we look at something like DeepSeek, in their inference report, they deploy DeepSeek R1 in the decode phase over 20 nodes. So they use expert parallel 144 to actually deploy the model. This is a extreme deployment, of course, but even at a smaller scale, we can deploy DeepSeek R1 using Llama 4 Maverick, over 4 nodes, with EP32. Using this DP-EP setup, which is much more efficient from a communication kernel perspective. Basically, this dispatch and combine operation are the key kind of kernels that are needed, and these are sparse operations, so they can scale well to this multi-node setup. There's also a bunch of key optimizations inside of VLLM that are useful for the expert parallel regime. One really key important thing is each one of these experts, we need to balance the load across these as efficiently as possible. So one of the key optimizations we have in VLM is called expert parallel load balancing, where we can replicate the most popular experts and basically use these to certain experts will be more popular than other experts. This is just empirical fact that you can see when you look at the models. And so expert parallel load balancing is a really, really important optimization, which basically duplicates individual experts to be able to make sure that the overall load is even. Another really important optimization is something that's called dual batch overlap. Basically, inside of the model, the collective operations, so like this dispatch combined operation, uses the networking, right? So this is a collective operation, which is going to be utilizing the InfiniBands or Rocky kind of, high performance networking between the nodes. And then the attention and expert layers are going to be using the compute units inside of the nodes. And so one really important optimization for the setup is to try to hide the collective operations by doing them in parallel with the computation operations. And so we can do this by actually taking every individual batch that's running, splitting that batch in two, and then executing those batches in parallel. And with some clever techniques, we can actually overlap the computation and the collective operation, which again helps to improve performance. And so in llm-d, one of the really key things that we do is to integrate all of this complexity associated with deploying the multi-node VLM instances, leveraging some primitives in Kubernetes called leader worker set, which basically allows us to deploy multiple nodes, multiple pods of VLM that span multiple nodes, and have these all connected to be able to do, data parallel attention, expert parallel MOE. This was a very, very quick introduction to expert parallelism, but this is a really important optimization for these really large mixture of expert models, and it's something we've been working really hard on in llm-d to make it consumable and easy to use. So thank you very much for coming today. Just to summarize, we really see the distributed optimizations as a key, kind of next layer of optimization that goes beyond the kind of naive deployment and service that you might see in most common deployments of VLM today. The overall idea is to try to exploit all the kind of key optimizations that we know are being done by large scale providers. Not every one of these techniques is going to be useful for every deployment. So I don't want everyone to leave this thinking, okay, wide expert parallelism, multi-node deployments are going to be needed for every single model service that's being run. We call these well-lit paths because they're trying to pave the way for, if you're serving DeepSeek, hey, here's a technique that you can use. If you're serving a mixture of experts models that's prefill intensive workload, and you want to introduce a bit more complexity in exchange for performance, you can try a prefill decode disaggregation. Some of the features are really useful in all cases, load balancing, KV cache management. These are techniques that can be used even for, serving a 0.5 billion parameter model. So there's lots of different paths, and all these some of these techniques are going to be useful for some use cases. Some will be useful for all use cases. But the overall idea with llm-d is to try to bring together the cluster scale performance optimizations and make them easy to consume through Kubernetes. So happy to answer any questions. Please feel free to reach out to me on Slack. And thank you very much for taking the time.